AI image generation is taking the world by storm. It's clearly one of the most important developments in AI over the last 12 months. The capability of these models to take a piece of text and generate a really beautiful picture is astounding. It's a huge development in how humans create images, how humans create art, and it's unlocking a lot of creativity of not only painting new images from text, but also editing images, turning childhood drawings or child drawings into, higher fidelity images. There's a lot of creative paths that people are taking with this. And we're only scratching the surface in terms of its capabilities. If you've been wondering how these models work, then this video is for you. My goal is for this video to be the most accessible description of how AI image generation works, even if you're not technical. We'll look at the various components that make up the AI image generation model called Stable Diffusion, and we'll talk about how they're trained and how they work together. Now, for this video, I've created tens of graphics and visuals that explain the various components. You'll find all of them in this article on my blog that we'll be going over in this video. So if you want to go back or dig deeper into them or recall one of the visuals or one of the concepts, you should definitely go to the article on my blog. With this, let's learn about AI image generation. So this is the illustrated Stable Diffusion. It's the article that I wrote explaining Stable Diffusion and how this model works. It took me a long time to really understand the various pieces, and it requires parsing through a lot of technical content, a lot of math formula, a lot of code. But then from all of that research, this is the most gentle approach that I can think of to explain how these models work. Now, it starts very general, but it gets a little bit more technical towards the end. So the more curious you are about, how deep you want to learn and understand these models, the more depth and content we'll get into that technical depth later in the video and the article. But you don't need to be technical at all to start. So this is the first, let's say, visual, and it's, one of the main ways to understand how these models work is that you give them a piece of text and they generate an image. So they're trained in a certain way to understand the text and generate an image as a result of that. Now, they also work in this other way. So this first way, this is referred to as text to image. But they also operate in a different way called image to image, where you can give them both an existing image and some piece of text, and they can edit that image for you. So if we tell it a pirate ship and we give it this image, it will, think of how it can see a pirate ship or how it can edit this image to create a pirate ship in it. And that is pretty impressive. So now that we know, as a black box, how the model works, how it operates, let's get a step deeper into the components that make it up. So at a very high level, you can think of Stable Diffusion having two components, an image understanding component and an image generation component. You see three major colors here. I'm still showing you the two components, but then the image generation component is also made up of two components, and we'll get down to them. Now, what happens between these components is that the text encoder, or the image understanding component, it parses the text that it got and it sends a representation. So if you know anything about NLP or language models, these are token embeddings. So these are numeric representations of the input prompt. And it hands those over to the image generator that uses them then to inform what kind of image it creates. Now let's talk about the image generation component. Now I call this the image information creator. This is not a technical term. This is just something I came up with to make it easier to understand what this component does. And what this component does, and what the image generator is composed of, is these two components. One is this image information creator, which creates information about the image. And then there's an image decoder that paints the final image using that information that was created in the previous step, in the pink step here. These are the three major components that make up Stable Diffusion. These three: the text understanding component, and then this component for creating information about the image, and then this image decoder that paints the final image. And then this is a great graphic to think about how Stable Diffusion is not really one model. It is multiple models, and these are, three different models. These are three different neural networks that are sort of trained on in different ways. But then at the end, they're trained jointly so they can work together. But then here you can start to understand what the components are, and then the rest of the video and the article go into how each of them works and how each of them was trained, and then how they were put together so they can work together. So it starts with the image information creator, and which is where a lot of the image creation happens. The image decoder is this idea that was added to the Stable Diffusion paper specifically to make the generations faster. And then the text encoder is a language model that also has a sense of imagery. To get a little bit more technical in describing these components, the text encoder is better called clip text. So there's this model called Clip. It was released by OpenAI, and it's a model that has two models inside of it, actually. There's a text encoder, and then there's an image encoder, and they work together. We'll talk about Clip and how Clip is trained, but this text encoder is the Clip model. And its output is these, at least for Stable Diffusion version 1, is 77 token embeddings. So your prompt is only understood up until 77 tokens. You can think of a token as a word, but usually tokens are parts of words. And so if you're dealing with Stable Diffusion 1, 1.4, 1.5, it cannot really, your prompt cannot be very long. So it can't be more than, 50 words. That can probably get us to 77 tokens. And then each of them represents, part of the input prompt, and it's in 768 dimensions. Now, where a lot of the image creation happens is here, which is what we started out calling the image information creator. But the actual technical term is this is a convolutional neural network. It's a type of neural network architecture called a unit. And it has another component that works with it and regulates a little bit of how it works, called a scheduler. And then the image decoder is one component of a neural network called an autoencoder, which includes an encoder and a decoder. We'll talk about how it's trained in the end. But then once you're generating an image, this is how the interplay of these various components. So you have your input text, your input prompt, that goes into the text encoder. It encodes the tokens. It breaks down the tokens of the input prompt into tokens. It hands that off to the information creator, to the unit in the scheduler, which does a bunch of crunching, packing a lot of, let's say, visual information into this other array with these dimensions. And then that array, in the end, this happens over a number of steps. These are called diffusion steps. We'll go over that and what it is exactly. But then the end result is this array that is then passed to the image decoder, which outputs the final image. And here you can see this is 3 by 512 by 512. So these are pixels, and 3 because it's red, green, and blue. And these dimensions, this is just pure information. It's not, it can't directly be viewed as an image, although there is some work that explains it as imagery. Now you know the major components. If you're curious how they're trained and how they work together, stick around. Okay, so you've heard about this idea called diffusion, that these AI image generation models are diffusion models. What does that mean? Let's see how that works in, not training, we'll get to training later. Let's look at it in the actual image generation. So when a trained model generates an image, what is the process? What is the diffusion part of that process? So this visual explains it, digs a little bit deeper into it. So our prompt goes into the text encoder, as we said, has the token embeddings, and then the diffusion process. So here I call it diffusion, but technically there are two better terms for it. So one, this is called the denoising process, but it's also called the reverse diffusion process. But what happens here is that it starts out with a random array, as a random image of noise, and then it packs a lot of relevant information from whatever it learned, as informed by the token embeddings. So if we want a picture of a beach that looks like a paradise. We start here with a random image that looks like noise, and then over a number of steps, this component packs more visual information into it, so that the final array here, the final collection of numbers, have pack a lot of information that makes the image decoder paint this image of a beach. We can sort of visualize this process to see that the initial tensor or array, we can visualize it. We can pass it through the image decoder, and it looks like this. It looks like noise. But then after it was processed, it looks like an image. So the image decoder is the way that we can translate between this information space of arrays to this visual space. We mentioned that it happens in steps, and this is kind of what the steps are. And if you go to, Dream Studio, which is where I do a lot of my Stable Diffusion generations, it has a slider for number of steps. These are the steps of denoising, where the image information is packed together and generated. So you have a random noise here, and it goes through, one step, and then another one, and with each successive step, there's better and better information there to help paint the final image. We can also visualize this process, this reverse diffusion, this denoising process of removing the noise. So if we take the results after step 1 and step 2 and 4 and 5 and visualize them the same way we did in the past, we can see that we start with this noise, and then it gets, it's also noise here, but then the noise starts to reveal a picture. And the picture successively gets better and better and more, beautiful. This is another video that shows that process. So this is, just the first few steps up until 50. It's quite breathtaking to look at. I really, enjoy taking a look at that. And you can see that after each step, the model improves the image a little bit and gets a little bit more detail. You can see this special thing happening between these two steps, step 2 and step 4. So you can see how this noise reveals the imagery. So you can see that this sort of green part of the noise, it's as if the model was squinting and saying, this looks like, some sea, and this is probably a part of a beach, and then this is probably like a tree. And then from that, the creation happens, the image creation happens. And that is, again, informed by the input prompt. It's like the model is staring at this slice of noise and having the text or prompt in its memory, and it's looking at, okay, how can this noise be translated into the image of a beach? And this is how that works. Now that we've seen how the image creation works, we can get into how the training is done, how this model is trained. So to understand diffusion, so this is the forward diffusion process. This is how we actually train these models, or train the pink part of the model, which is the image creation, or the unit and scheduler. Best way to try to sort of explain this is that, we have a lot of images. We can get a lot of images and their captions, which will be useful later on from the web. And so that's how these models are trained. So we can take an image, any image. We can generate noise randomly. We have algorithms to create noise. It's very easy to do. But then we create some sample of noise. So 1, we take our image, we take a sample and image from our dataset. 2, we generate noise, and then we apply that noise to the image in some amount. So we have 3 or 4, let's say, examples here. So no noise, all noise, and then some levels in between. And then we add that noise to that image in that amount. And that is a training example. We can do that again. Another image, another sample of noise, and then another amount, and we apply that noise in that amount, and then we have another noisy image here. From here, we can create this data set. So we have an input data set of, okay, this is a noisy image. This is the amount of noise applied to it. And then this is the actual sample of noise. And, this is generated, so we know this. And, we know all of these. And so this kind of becomes a supervised learning exercise. So we have our inputs, we have our outputs, and then we train a model to be able to predict the noise that we added here. How do we train it? We have computer vision models we have really strong machine learning and learning algorithms that are able to learn the relationship between this input and this output. And if we have enough examples of images, this model is going to be able to, let's say, create images or paint images by removing noise. So this is the data set that this image generation component is created using. Now, let's look at what a training step is. We take an example from our data set, which is a noisy image and then amount of noise. So these are the inputs. We give these to our UNet, to our neural network that does computer vision, and we ask it to predict the noise. And, in the beginning, it will not do it correctly, but we have the actual label and noise, and we say, okay, you predicted this. No, the real answer is this. So we can calculate the error, which is like the difference between them, and then we update the UNet using that error. So this is the classic machine learning update rule of like, this is the label, this is the loss function, this is how off you were, and then we update the model so that, the next time it comes across an image like this, it has a better idea of what the noise distribution is like. So this is the basic machine learning step, and this is how it's applied here. So now we know how this UNet is trained. Let's see how that trained UNet paints images, because this is, let's say, the reverse process. So it works kind of like this. So we start with this completely noisy image. Let's say here, for example, the noise amount, the largest noise amount is 3. Really, it's between 0 and 1, like the fractions. But for example, I'm just using 1, 2, and 3 here. So let's say we have this is a completely noisy image. And then we say this is the most noise that we have. We give it to the model predicts the amount of noise that is in this image. So given that we have the original noisy image, we have the predicted noise, we subtract the two, and then we get a slightly denoised image. So effectively here, the model has painted something. It has painted a version of the image, but it's not the final image yet. It's only one step there. From here, we can say, okay, so now we removed noise amount number 3, we removed a little bit of noise. Let's go back and say, okay, now the noise amount is 2. Let's predict that noise and remove it a little bit. We get a more clearer image. And then we are at noise amount 1 now. And then let's predict that, subtract it again, and then we end up with the final image. And so we start here with the completely noisy image, and then we generate the final image here. Now, one innovation that the Stable Diffusion paper introduces to AI image generation is to make it faster by using this autoencoder. So the autoencoder can be trained kind of like this. It's a kind of a model that takes an image, compresses it to a much smaller array of information, and then has another component, which is a decoder, that then decompresses that or decodes that and tries to reconstruct the original image. And so this is a model that can be just trained by having lots of images and comparing the original with the, let's say, the final uncompressed version. It compresses it, then decompresses it. And by having this compression decompression process, by applying it to the image generation, a lot of this diffusion happens in a much smaller space. So the arrays that are being diffused or denoised when we're generating a picture are, let's say, much smaller arrays, and so models can do them much faster. And so this is how Stable Diffusion compares to some of the models previously that were not doing this encryption step. They were operating in much larger spaces of the actual images, and that made them slow. So by working in the compressed latent space, Stable Diffusion makes this faster. So instead of generating the images in the noisy images on the actual images, it works on these latent or compressed versions of them, where we pass it through this encoder, and then we have our compressed version of it, and then these are the amounts of noise that we add, not to the original image, but to the actual latent or compressed version of the image. And so this is an image that's important if you've read the paper, if you want to read the paper. So At the top here is more about how the training process is done. So we have an original image, we encode it, and then we can generate examples from the various compressed, latent versions of that image, and with different amounts of noise applied to them. And then when we're generating an image, we start with complete noise, we denoise it for a number of steps, and then we pass that final processed image information array by the image decoder, and that generates the final image. And this visual is my version of this visual from the paper. So this is a little bit of what happens here, and this is how, it is described in the paper. And, as like general research visuals are like, they pack a lot of information here, and people who are generally reading this, they have a little bit of a background on the various terms used here. The one component that we'll get to here is this conditioning. So the conditioning is how we have the text, which is the input prompt here. That's how that factors into this denoising process. Okay, so now we looked at how Stable Diffusion generates images from noise to an image, but we didn't at all talk about how it uses text. We only now really know how to create random images. So if we train this model and deploy it, we'll not be able to guide it to say, okay, draw an image of a cat or a dog. It will generate images that seem like images that it was trained on. So if it was trained on, logos, it will create just random logos. If it was trained on cats, it will generate random cats. But now we need to learn a little bit of how do we get language involved here? How do we train the model so it can first understand the prompt, quote unquote, because it's not complete understanding, it's some kind of understanding, one. And then two, how does it include that understanding in the image generation process? So to understand that, let's look at the text encoders. So Stable Diffusion has a language model, which is the text understanding component of it. The initial paper used BERT. The final model uses clip text. Now, the language model is important. I talk a lot about language models. You can find more about language models in my channel and blog about GPT and BERT and all transformers and all of these kinds of models. And it turns out, as we've learned from the Imagen paper from Google, that the language model is one of the most important components of the image creation model. And this is a graph where they've varied the size of the language model, and that had a major effect on how people liked the final images that were created. And in this earlier version of the article, I point to these teams training a new clip model, much larger, and I anticipated that future versions of Stable Diffusion will use this much larger clip model called OpenClip. And true enough, Stable Diffusion 2 uses this model. Now, how is clip trained? So let's start by looking at the kind of data it is trained on. So it's a collection of two things, images and text that describes that images. You can think of that as captions, although, in some of the data sets, like the original one, it's like the alt text part of the HTML that was part of this. So these are examples from this data set that we link to here, which is, the image and its description. So, and what clip does, it tries to embed, embeddings are these numeric representations of things. So clip has two models, one that embeds images, so represents images numerically, and another that embeds text numerically. And its goal is that it makes similar images and text represented by similar vectors. And so, let's see if I have an example here. Okay, so an example is if I have an image of a dog and then a sentence that says this is an image of a dog, let's say, the vectors representing these two should be closer to, an image of a cat. And closer is, using things like, similarity metrics that we have. It's part of basic, let's say, linear algebra. How clip is trained, however, can be simplified as this. So we've collected the data set. Let's say we take one image and its caption and we embed them both. And then we have the model predict, the image embedding and the text embedding, are these similar or not? And we know they're similar because this caption is of this image. So that's how we chose these examples. And when we start to train the model, it will say, they're not similar because the model is not trained. It's not projecting them to similar spaces in its, let's say, numeric representation space or embedding space. So it will predict, no, these two are not similar. It will assign them vectors that are not similar. But we know that they are similar. So what we do here is that we calculate the error, just like what we did before. This is, again, the simple, usual machine learning step of saying, okay, you were wrong. You were wrong by this much. You need to, update your various parameters so that the next time you see an example like this, you are closer to the actual right prediction. And so we continue doing this with all of our examples, with all of our images. And we can generate a lot of images because what we did here is if we give it an example of an image and its own caption, but we can also give it another caption or the caption of another image and force it to say that these are not similar. So we need both positive examples and negative examples. And with that, that's an idea called contrastive learning, which is a very important idea in machine learning. And with that, we create this, let's say, embedding model that embeds images and text similarly in, let's say, the same space. Now that we have CLIP, we have this model that sort of ties together language and imagery in the same space. We can bring it into the picture and train it jointly with our other components that we've already looked at. And that kind of looks like this. So now our unit, our noise predictor, doesn't take only two inputs, it also takes a third one, which is the text prompt or the token embeddings of the text prompt. And it uses that because that contains information that would help it predict the noise here. So if this is complete noise and we say, okay, this is an image of a dog, it'll try to squint at the image and say, okay, what noise can I subtract from here? And this is not conscious thoughts happening inside of the model, but this is how we're framing the problem, and our learning algorithm is gonna nudge our model in a way that applies this process. And with this, we can see the final shape of our data sets here. So we have the step, or amount of noise is a better term. So on step, this is from a previous version. I didn't update this one. So this is better called the amount of noise here. And then this is the, not the image, but the noisy compressed version of the image with various amounts of noise applied to it. And this is the text prompt used for it. And then this is the predicted. And so with this, we train our unit and our image creation component unit plus scheduler. The final sort of idea is about just how exactly inside the model this is generated. And so there's a layer of attention that happens in between unit predictions, and that's the layer where the amount of the information from the text prompt is added. So this is just a final detail that I conclude this article with. So if you want to learn more about attention, be my guest. By previous blog posts talk a little bit about its evolution, about how it works in transformers. But then if you've made it here, congratulations. Now you know the major ideas about how image generation works and what kinds of data sets it's trained on and how it's trained on them and its various components. I hope you found this useful. Let me know if you have any questions in comments, or send me messages or tweets on Twitter. Thank you for watching. Please subscribe and like, and I'll see you in the next video.